Hi, my name is Jeff Squires. I work for Cisco Systems, and I'm one of the developers in the Open MPI project. This screencast is about OpenFabrics concepts. There are several things you need to know about OpenFabrics in order to be able to optimize Open MPI and your application running on top of an OpenFabrics network. Let's go through some of them. The first one that you need to know is the Verbs API. This may be an acronym you've heard before, sometimes referred to as VAPI. The IB and IWARP actions are generally known as verbs. There's a send verb and a receive verb and various others. The first InfiniBand VAPI was the Mellanox VAPI, or MVAPI, and that's now pretty much deprecated. As a matter of fact, Open MPI version 1.3 doesn't even support that anymore. OpenFabrics has a slightly different VAPI. It's similar concepts, but a slightly different set of API calls. So this is the VAPI that Open MPI supports, the OpenFabrics VAPI. In OpenFabrics networks, there's no such thing as an unexpected receive. All messages must be expected, meaning that the receiver has to pre-allocate resources, such as you have to put a pool of buffers to receive messages, or a pool of buffers as a target for RDMA or something like that. Unexpected messages triggers errors. And so that's something that underneath the covers OpenMPI has to manage, but it is something you need to know for tuning some of the finer characteristics of OpenMPI with OpenFabrics networks. OpenFabrics networks also have virtual lanes and service levels. Basically, the traffic is divided into virtual lanes. So it's basically an extra tag that's on every fragment that goes out across the wire. It's kind of analogous to MPI communicators, but a much more basic level. And you can do things with those virtual lanes, such as assign quality of service-like attributes, waiting for bandwidth, and things like that. Service levels map to lanes as well. I'm not going to go into it in too much more detail here, but that's the general 50,000-foot view of this. Now, OpenFabrics is run by a bunch of queues. The very basic thing is a queue pair, or a QP. It's a unit of connection in OpenFabrics. You can think of it as sockets for OpenFabrics. It's not really the same thing as TCP sockets, but if this is your first introduction to OpenFabrics, it's enough to draw that analogy in your head. Now, a queue pair is, as it implies, two queues. One's a send queue and one's a receive queue. So I have a send queue that's connected to the receive queue on the other side, and the other side has a send queue that's connected to my receive queue. There's also a completion queue. Most of the OpenFabrics verbs are non-blocking, so when I do a send, it really just starts the send, and I have to check later to see when that send actually completed. And one of the ways I can know that is by checking the completion queue to see if an event has come on that says, oh, that send you started a while ago has completed. And also a very important concept in OpenFabrics in general, RDMA-based networks, are registered memory. So it means that since the RDMA networks are directly sending and receiving from RAM, and we don't involve the main CPU, I mean, that's kind of the whole point of an operating system bypass network, there's an issue here, because the operating system may actually change the physical to virtual RAM mapping at any time. And so where the RDMA network is sending from may physically move in memory if the operating system chooses to, say, page something out or page something else in, or just move something within physical RAM. So it looks kind of like this. So let's say that, let's take the situation for an InfiniBand network with a corresponding HCA on a server here. The same exact scenario is true for IWARP as well. So MPI says, hey, InfiniBand, will you send this buffer, please? And the HCA obtains the physical address of the message in RAM, and it starts sending. So you can see that it's reading out of RAM, and it's sending and putting out bytes onto the network. But then let's say that the operating system decides to change the physical mapping for whatever reason, and the physical location of the message in RAM moves. Well, now you can see that the HCA is sending garbage, and that's no good. So the solution to this is what's called registered memory. You basically tell the operating system not to change the physical to virtual mapping. And sometimes it's referred to as pinning memory or locking memory as well. But basically it guarantees that the operating system will never move the contents of that memory to a different physical location until you unregister the memory. So really, registered memory is two different things. It pins the virtual to physical memory, and it notifies the HCA or the NIC, in the IWARP case, that of this mapping, so that they can know when I see this virtual address, it really means this physical address. Now, there are some problems with registered memory. Number one, it's slow, and particularly in a high-performance network, that's difficult. So OpenMPI has to do all kinds of things to get around the slowness of registering and unregistering. Another thing is that the operating system can only support so much registered memory at a time. Think of it very simply as this. When you pin a page, it becomes unswappable, right? And so not only, I mean, you're bound by the physical amount of RAM that you have, but then you have to subtract a bunch off of that for the operating system, which is unswappable already, and then any other supplemental libraries or daemons or things or, just general working space that you do need to be swappable, you will get something less than, your total physical RAM on the machine. So you have to be very careful to set the U limits properly. This is part of the OpenFabrics or the InfiniBand setup on your machine, and so this was likely done already, but it is something that we've seen a lot of users have problems with, that they forgot to set the U limits for registered memory to be unlimited, and therefore run into problems at runtime with MPI applications. So an obvious question is, well, how much registered memory does Open MPI use? And it's unfortunately a very complicated answer, and it requires a lot of background information, so we'll go through some of this here. For reference, there is a complete answer on our FAQ. I'm sure you can't read that URL there on the slide, but if you go onto the FAQ into the OpenFabrics section, there's a question about limiting memory registration, limiting registered memory usage. That's where the complete answer is. So more backgrounds so that we can answer how much registered memory Open MPI uses. A common trick that many MPI implementations do, we certainly didn't invent this, is that when you call send, MPI send, that underneath the covers we register the buffer, we being Open MPI, and then we do the send, but then we return and we leave that buffer being registered so that the next time you call MPI send with that buffer, we don't have to pay the cost. Remember, registering is relatively slow. So the next time you call send, we don't have to go through the slowness of registering it again. And it's great for benchmarks, particularly ping pong benchmarks where you're using the same buffer over and over and over again. It's usually not great for real applications. And when I say not great, meaning it has no benefit, because this really only has benefit if you're going to reuse the same buffers over and over again. Now, if your app uses the same buffers over and over again, great. If it doesn't, you continually send a different row in the matrix every time or something like that. This kind of trick is not as helpful. So for this and a variety of other reasons, OpenMPI does not do this common trick by default. You certainly can tell it to do so, but by default it does not. Now there are some problems with user memory registration as well. You can run out of memory, right? So remember I said before that the operating system only supports so much registered memory. So if you start registering, eventually the operating system is going to come back and say, nope, sorry, there's nothing more to be had. So MPI, therefore, has to implement all these eviction policies, and it gets kind of icky. The application can free the buffer. So this is a bad thing, that if I have registered memory, and then I call an application calls MPI send, gives us the buffer, we register it, and we return, and it's still registered, but then the application frees that buffer. Well, suffice it to say that if you free a buffer that is registered, bad things happen down in the kernel. So MPI basically has to intercept all the frees and sbreaks and munmaps and all these kinds of things, and it gets to be really ugly and horrible in order so that we can say, okay, calling free on that, is it registered? Oh, it's registered, I need to unregister it, and then actually let the operating system free the memory. This is extremely problematic. There's 3 different ways for us to intercept these calls in Linux, and every single one of them has been shown to break real-world applications. So this is another reason we don't do this whole leaving memory registered by default trick. So we just say no, unfortunately, except for benchmarks. I've given you a bunch of information here on background of OpenFabrics concepts. There's still more information available about this. Go into our FAQ on the website, into the tuning category. There's general information about tuning there. And then there's much more specific information about InfiniBand, iWarp, and OpenFabrics tuning on the OpenFabrics section of the FAQ. Hope this information was useful to you. Thanks.